Welcome back to Linear Algebra. I'm Dr. Jeff Groh. In our last lecture, we talked about linear systems of equations. There is a special class of linear systems that we can define. A linear system of equations, and these typically look like A11x1 plus A12x2 plus ... plus A1nxn equals B1, A21x1 plus A22x2 plus ... plus A2nxn equals B2. Let's suppose we have m equations in n unknowns, so we'll have a m1x1 plus a m2x2 plus ... plus a mnxn equals bm is said to be homogeneous. If all of the right-hand sides are 0. There are two correct ways to pronounce this word. One of them is homogeneous. The other is homogeneous, though there is a common mispronunciation of this word amongst mathematicians and also physicists and etc. You will often hear it called homogeneous. However, you homogenize milk, not equations. These are homogeneous or homogeneous. Homogeneous systems will be important in the development of our theory. If we have 2x plus 3y equals 0, 5x plus 9y equals 0, this is homogeneous. Why? It's a linear system, and all of the right-hand sides are 0. It doesn't take very much imagination to figure out at least one solution to every homogeneous system. In this particular problem, the point 0, 0 is obviously a solution. The point x1 equals 0, x2 equals 0, to xm equals 0 will be denoted by 0 with a little half arrow over the top. We call this the 0 vector. We can write down the following theorem immediately. Every homogeneous linear system is consistent. That means every homogeneous system will have at least one solution, if not infinitely many. In particular, the 0 vector is always a solution to a homogeneous system. And this is basically the proof. You plug in 0, you get a true statement for every single one of the equations in the system. I'd like to give you some examples of applications of linear systems. Suppose that we react hydrogen gas and oxygen gas. And let's suppose that these produce water when they react. As we know, chemical equations require balancing. You have to have the same number of atoms of a particular type on one side of the chemical equation as on the other. So if we're going to have, say, X hydrogen molecules added to Y oxygen molecules, getting Z H2O molecules, what are the values of X, Y, and Z that balance this equation? Here we have two X hydrogens. That's going to be equal to 2 Z hydrogens on the other side of the equation. Also, Y times 2 oxygens appear on the left-hand side of the equation. That must equal Z oxygen atoms on the right-hand side of the equation. As you can see, we here have two equations in three unknowns. This is underdetermined. When you think about it, chemical balancing equations must always be underdetermined because it should also balance if you multiply through by any whole number. Now, we can solve this equation, this system of equations, by moving things around. You can see that we can cancel 2 off on this equation and get X minus Z equals 0. And also, we'll have 2Y minus Z equals 0. There you have it. It's almost in reduced row echelon form. To place the system into reduced row echelon form, we need to multiply the second equation through by 1/2. If we move these over, we'll have X equals Z, Y equals 1/2 Z, and we'll have solutions of the form X equals T, Y equals 1/2 T, Z equals T. If we want to choose T so that all of the coordinates, all of the coefficients in the equation are integers, we can choose T to be any multiple of 2, like 2, 4, 6, 8. All of those will give integers. But if we want to choose them so that we choose the smallest value of T that gives us all integers, we can choose T equals 2. That balances the equation so that we have 2 hydrogen molecules, 1 oxygen molecule, yielding 2 molecules of H2O. Note, however, that if we multiply through by any integer after this, we multiply by 3, 6, 3, 6, that will also yield a balancing equation. The smallest one, though, is 2, 1, 2. Note that we started off with a homogeneous linear system that was underdetermined. Homogeneous systems are always consistent. You can always choose 0, 0, 0. That equation balances too. It's just not sure that there are any reactants or products in that equation. However, we will always get, in an underdetermined system like this, non-trivial solutions. The zero solution is called the trivial solution of a homogeneous system. Before giving you another example, I need to make some definitions. A monomial is an expression of the form a constant times x to the power of n, where a is just some real number and n is an element of the set of whole numbers. the whole numbers include 0. They contain the natural numbers as a subset. The natural numbers are denoted by a blackboard bold N. Note, a constant is a monomial because you can think of that as 7 times your variable x to the power 0. Remember, the exponents for monomials can include 0. They can't include negatives. So 7x to the negative 1, or 7 divided by x, is not a monomial. Seven is a monomial. Just like 7x squared is also a monomial. 7 times x to the power of a whole number, any constant, times x to a whole number is a monomial. Now, a polynomial is a finite sum of monomials. In particular, a power series is not a polynomial. Power series would be infinite sums of monomials, not finite sums. So for example, p of x equals 2x squared plus 3x minus 5 is a polynomial. The degree of a polynomial is the degree of the highest degree monomial in the sum. So this would have degree 2. If I write, say, sine x, which I know to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus so on forever, this is not a polynomial. It is a power series. I'd like to introduce some notation. Pn is the set of all polynomials of degree n or less. In other words, all of the elements of Pn look like a0 plus a1x plus a2x squared plus dot 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 plus an x to the n. We are not precluding the possibility that the coefficient a sub n is 0. You could have all of these be 0, in which case the polynomial would be the constant function 0, and that too is in p sub n. We can, for instance, define p2 to be the set of all a0 plus a1x plus a2x such that a0, a1, and a2 are all real numbers. If we want, we can extend the set of real numbers to the set of complex numbers, or we could even use other fields. One thing to point out, polynomials of degree 2 or less have 1, 2, 3 independent constants. Let me give you an example. Let's find a polynomial passing through the points 1, 1, 2, 1, and 3, 4. If I'm dealing with a polynomial of degree 2, there are 3 unknowns to be determined: the constant term, the coefficient of x, and the coefficient of x squared. That takes 3 pieces of data about the curve. So if I'm looking for a polynomial that passes through these 3 points, I should at least consider quadratic polynomials. These 3 points can determine 3 pieces of data Those will give us the three constants. In our solution, we'll let our polynomial be called p of x. It's going to be a0 plus a1x plus a2x squared. We want this polynomial to pass through each of these 3 points. That means when x is equal to 1, y is equal to 1. If I plug in x equals 1, I get a1, a0 plus a1 plus a2 equals 1. If x is 1, you output 1. If x is 2, you also output 1. So when x is equal to 2, I'll have a0 plus 2a1 plus 4a2, and I'll output a y value of 1. If x is equal to 3, I need to output 4. That'll be a0 plus 3a1 plus 9a2 equals 4. Notice that I have 3 equations in 3 unknowns.
We need to enter the coordinates of this matrix into our calculator. So I'm going to press second and then matrix. We need to edit this, so I'll go over to the edit and hit enter. Our matrix is 3 by 4. The coefficients then were 1, 1, 1, 1, 1, 2, 4, 1, 1, 3, 9, and then 4. We need to find the reduced row echelon form, so I'm going to go back to second matrix and go to math this time. I usually scroll up from the bottom to get to the reduced row echelon form, hit that, and then go back to second matrix. It's the first one, so I'll just press 1 and then hit enter. Notice that we have these nasty fractions. I want to get rid of those fractions. And so what we'll do is we'll hit math and then frac and then just enter. That converts everything into nice fractions for me.
I put the augmented array into my calculator and hit RREF, and then math frac to produce fractions after that. It gave me 1, 0, 0, 4, 0, 1, 0, negative 9 halves, and 0, 0, 1, 3 halves. That means that my polynomial function is 4 minus 9 halves x plus 3 halves x squared. That polynomial will contain the points 1, 1, 2, 1, and 3, 4. I would like to introduce you to another example involving traffic flow. By the way, these problems are always similar to electrical circuits for reasons that will become apparent in a moment. Let's consider the following diagram where we have certain nodes. These nodes are intersections, let's say, for streets. Suppose our traffic flow follows this sort of pattern, and we have little arrows on these. Let's suppose that we have 200 cars per hour entering this road, 300 coming out this way, 50 per hour coming out this way, and 450 per hour coming out this last route. How many cars are traveling on the various streets in between? Well, we don't know. Let's give them variable names until we can figure this out. Let's call the traffic going this way on the top road x1, x2, x3, x4, and x5. Now, unless something very unusual happens, the number of cars going into an intersection will equal the number going out. It's very unusual for cars to either appear or disappear in the middle of an intersection, though I'm not saying it's not possible. In fact, one time I was traveling with my family along the Freeway 210 north of Los Angeles on, I think, the day before Thanksgiving, which is a terrible day to commute. And we had traffic backed up for miles, and we could see helicopters hovering over the road some miles down. Come to find out, what had happened is that a cement truck had been going over an overpass and had careened off and fallen down into the freeway below, which was a very bad day for the next two cars on the freeway. Now, in this case, we had a vehicle, a cement truck, appearing from nowhere, right into the middle of the freeway. That's a very unusual circumstance. Let's suppose that doesn't happen here. The number of cars going into the intersection is equal to the number of cars going out. So if we have 200 going in, the number going out will be x1 plus x2. We can perform this exact same analysis on all four intersections. So on the intersection to the top right, we'll have x1 plus x3 equals 50. On the lower left, we'll have x2 plus 300 equaling x3 plus x5. And then on the lower right intersection, we'll have x4 plus x5 equal 450. This gives us a system of 4 equations in 5 unknowns. We know going in that this will be underdetermined. I'm going to express this system of 4 equations in 5 unknowns as an augmented array. We'll have 1, 1, 0, 0, 0, and then the bar where the equal sign would be 200. That takes care of this first equation. The next equation is 1, 0, 1, 0, 0, and then 50. That takes care of the second equation. I need to move this one to the other side. We'll have 0, negative 1, 1, 0, 1, 300. That takes care of this equation, and then finally 0, 0, 0, 1, 1, and then 450. I will calculate the reduced row echelon form using my calculator.
We need to enter the matrix, so we're going to edit, and this was a 4 by 6, so it's 4 enter, 6 enter. Now we have to enter all of the entries into the matrix. 1, 1, 0, 0, 0, and the last one was what? 200? Followed by 1, 1, 0. We have 300, followed by 1, 0, 1, 0, 1. Okay. Zero, 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 1, 1, and 450. Aha. Now that we have the matrix entered, we need to calculate the reduced row echelon form. So we'll go to Math and then scroll up from the bottom, RREF, and back to our matrix A. I always put it in the matrix A unless I already have something there. And here you have it in reduced row echelon form.
We obtain this reduced row echelon form, from which we see that one of the previous equations must be some combination of the other equations. By doing elementary row operations, we can make one of the equations become 0 equals 0. So it was already dependent on the other 3. We have 3 dependent variables and 2 free variables. x3 and x5 end up being free variables in this case. x4 will depend upon x5, x2 will depend upon x3 and x5, and x1 will depend upon x3 and x5. In order to close this system, we need not one additional piece of information, as you might have thought from the original system of 4 equations and 5 unknowns. You need 2 pieces of additional information in order to close the system. It doesn't have to be x3 and x5 that are given, but it will make it easier if we do. Suppose we lay down those little rubber air hoses that across the road and determine the traffic flow along the roads x3 and x5. And that we find x3 is 50 and x5 is 200. Then what are the other variables? x4 will be 450 minus x5, because this equation represents x4 plus x5 equals 450. That means x4 is 450 minus x5. When you bring those over to the other side, they become minus. That tells us then that x4 will be 250. x2 may be determined by the second equation. It's going to be x3 plus x5 plus negative 300. These add up to 250. When we bring them to the other side, we'll have 250 and negative 300. This gives us negative 50. In other words, x2 we had going down. The net traffic flow is going to be going the other way, up, and it'll be 50 cars per hour. That leaves us with only x1 defined. It's going to be 500 minus x3 minus x5. If you take 500 and subtract 50 and then subtract 200, you get 250. So by specifying 2 additional pieces of information, we can figure out all of the traffic flow on the other lines. By calculating the reduced row echelon form, we could even tell which variables were easiest to specify, where to put those rubber hoses in order to determine the traffic flow on the street, and how many rubber hoses to place. For electrical circuits, we have some important principles, such as Kirchhoff's current law, which says that the currents going into a node in an electrical circuit will equal the currents going out. In other words, if we consider currents going out to be negative currents and currents going in to be positive currents, then the algebraic sum of those currents will be 0. The sum of currents into a node is 0. Ohm's law says that if you have a resistor of some resistance R measured in ohms, and if you have a current I going across that resistor, then the voltage drop across the resistor is the resistance times the current. In Ohm's law, the voltage will be measured in volts and the current in amps. There is a third law that is important in this section, and that is the sum of the voltage drops around any closed loop in an electrical circuit will be 0. voltage applied by a battery would be a negative voltage drop, if you will. In other words, the voltage drop across all resistors added up will have to add up to the amount of impressed voltage by the battery. There are a number of examples of electrical circuits given in your book, and I'll leave that for you to read. I would like to move on to matrix algebra. What is a matrix? A matrix is a rectangular array. Arrays more generally don't have to be rectangular. You can have any number of elements in any row or different numbers of elements in different columns, but to be a matrix it has to be a rectangular array. A certain number of rows and a certain number of columns, and every row has the same number of columns, and every column has the same number of rows. We are going to assume that the matrices that we use have real numbers as entries, or at worst, complex numbers. I would also like to disabuse you. A lot of students try to invent the word matrice, but I assure you, there is no such word. Remove it from your lexicon. The singular form is matrix, and the plural form is matrices. There is no such thing as a matrice. It doesn't exist. You will only make yourself sound ignorant by using the non-word matrice. A little bit of notation. We often denote a matrix by a capital Roman letter, say capital A. It will have entries A11, A12, through A1n, A21, A22, through A2n, AM1, AM2, through AMN, and we will often abbreviate that by just writing AIJ. If the double subscripted letter AIJ is inside of parentheses, we are referring to the entire array, the matrix. If it is outside of parentheses, we are referring to a particular entry in that matrix. So whether we surround it by parentheses or not will make a difference. In this notation, I is the row number. J is the column number. A m by 1 matrix is called a vector, or even a column vector. However, I want you to be careful. If you use the word vector, you specifically are referring to a column vector unless you otherwise indicate. You can talk about a 1 by n vector, in which case you should definitely call this a row vector. If you're referring to a row vector, you must include the prefix or the adjective row. As we go through this course, you will see that we will use the word vector in many instances, and almost always we will refer to a column vector. Those are going to be the standard case. The order of a matrix is a number m by n, where m is the number of rows and n is the number of columns. So for example, if I have 1, 2, 4, 0, 7, 9, this matrix is 2 by 3. What do we mean when we say two matrices are equal to each other? We say that matrices A and B are equal if, first, they must have the same order. If they don't have the same order, then they're not equal. Remember, they're of the same order if they have exactly the same number of rows and the same number of columns. And the entries must be equal. For all relevant I and j's. In this case, we're assuming I goes between 1 and m, and j goes between 1 and n, if these are m by n matrices. So in other words, we say that corresponding entries are equal. How do you add two matrices? Well, first, they have to have the same order, or else the addition is not defined. But if they do have the same order, you just add the corresponding entries. I'm getting at here, when I add A and B, I get the matrix where the entries are the sum of the entries of A and the entries of B. So for example, suppose I have the matrix 1, 3, 0, 2, 5, negative 4, and to that I'm adding 3, negative 2, 1, 4, 5, 6. That gives me 4, 1, 1, 6, 10, and then 2. You can also add using your calculator, but on something like this, what's the point? What do I get if I try to add 1, 2, plus 3, 4, 5, 6? Well, this matrix is 2 by 1, and this one is 2 by 2. They are not of the same order, so the answer is undefined. It is also possible to rescale a matrix. C times a matrix Aij. How do you calculate a scalar times a matrix? Well, you just rescale all of the entries. This is a definition. It tells you what we mean when we take C times a matrix A. So for example, if I have 3 times 1, 2, 4, negative 3, what I get is 3, 6, 12, negative 9. We simply multiply all of the entries by that scalar. Now that we've defined these two operations, matrix addition and scalar multiplication of matrices, we need to know what algebraic properties are permissible and which are not. Well, first of all, addition of matrices, provided it's defined, is closed. If I add an m by n matrix to an m by n matrix, I will get an m by n matrix. So the set of m by n matrices is closed under addition. This is called a closure law. There's also an associative law of addition. A plus the quantity B plus C is equal to the quantity A plus B plus C. There is the commutative law of addition. I'm writing these names out and reinforcing them because I would like for you to understand and know the names of these properties. These are not very sophisticated properties. These are very simple ideas, but you should know them. I bet you thought we were done. I'm going to include 10 properties in this list, so we're just getting started. There is something called the zero matrix. We'll denote it by a capital theta, and it will have all entries equal to 0. If this is m by n, it will have m rows and n columns where every single entry in every row and every column is the zero scalar. Now, if I take a matrix A and add that to the zero matrix, what do you suppose I get? I will, of course, get the matrix A. So this zero matrix behaves just like the zero scalar in the set of real numbers. If you add the zero number to any other real number, you will get that other number. 0 plus 2 is 2. Now, there do exist additive inverses, which allows us to talk about subtraction. If I have 3 minus 2, I can think of that as 3 plus the additive inverse of 2. What do I mean by the additive inverse of 2? It's the thing when I add to 2, I get 0. For each m by n matrix A, there exists an additive inverse B satisfying A plus B equals B minus or plus A, and that gives you the zero matrix. Notice I've said that there does exist an additive inverse, not that there is one and only one additive inverse. We don't need to assume that. We can prove it later on from the 10 properties that we're going to list. We will be able to show that for each matrix A there is a unique additive inverse. That will be a theorem. Therefore, in the future, the additive inverse of A will be denoted by minus A. As it stands right now, for all we know, there could be 12 different additive inverses to each matrix A. We'll prove later that there's only one. Okay, so we've seen the first 5 purely additive properties. From here on, they're all going to involve a little bit of scalar multiplication. First, the closure law of scalar multiplication. If A is a real number and big A is m by n, then A times big A is m by n. So just rescaling a matrix doesn't change its order. One times A, you guessed it, is A. So if you rescale a matrix by 1, it leaves it alone. There is, of course, an associative law of scalar multiplication. It goes like this. If A and B are real numbers and A is m by n, then A times B times the matrix A gives you the same thing as if you multiply the scalars together first and then times the matrix A. That leaves 2 more properties. First is distributive law number 1, which I guess the last one must be distributive law number 2. If A is real and A and B are m by n, then A times A plus B gives you the same thing as the scalar A times big A plus the scalar A times big B. You can distribute scalars across vector addition, which means you can also factor the scalars out, factoring being the reverse of distributing. In this case, we'll take 2 real numbers and a matrix that is m by n. Then A plus B times the matrix A is the same thing as A times big A plus B times big A. So you can distribute matrices across scalar sums. By the way, any set having 2 operations that satisfies the last 10 properties is called a vector space. That means that the set of n by n real entry matrices over the real numbers, being the set of scalars, is a vector space. I next want to define what I mean by matrix multiplication. If A is m by p and B is p by n, then we can define what we mean by A times B. This is by definition, so you're just going to accept this. It's going to be the matrix where the entries are the sum, as k goes from 1 to p, of A, I, k, B, k, j. Notice that we're indexing the columns here and holding the row fixed. We're taking the ith row of the matrix A and multiplying it by the jth column. We're indexing through the rows and holding the column j fixed. So if you take the ith row of the matrix A and multiply it onto the jth column, multiplying corresponding entries of the row times the entries of the column, and then add those up, that gives you the ijth entry in the product. Let me show you specifically what I'm talking about here. First, note that the product will have the same number of rows of the first matrix A and the same number of columns as the matrix B. So this yields an M by N matrix. Suppose A is the 3 by 2 matrix 1, 3, 4, 2, 5, 6. And B is the 2 by 2 matrix. Well, let's make it a 2 by 2. 1, 3, 0, 4. How do we multiply these matrices? It might be easiest if you put them side by side and then multiply the first row times the first column. We're going to have 1 times 1 plus 3 times 0. That gives you the entry in the first row, first column. First row times first column gives you the entry in the first row, first column of the product. If I take the first row and multiply it by the second column, I'll have 1 times 3 plus 3 times 4. First row, second column gives you the entry in the first row, second column. If I take the second row and multiply by the first column, that gives me 4 times 1 plus 2 times 0. And also now 4 times 3 plus 2 times 4. And then 5 times 1 plus 6 times 0, followed by 5 times 3 plus 6 times 4. Notice that I get a 3 by 2. These numbers have to match in order for the product to be defined. What you get will be a matrix of the order of M by N, the outer two. Let's continue on with this computation. We get A times B equals 1, 3 and 12 makes 15, 4, 12 and 8 makes 20, 5, and then 15 and 24 makes 39. I want you to study this example until you completely understand it. Matrix multiplication will underlie a lot of what we do from here throughout the rest of the course. So you will need to understand this thoroughly. Let's do another quick example. Let's suppose that I have 3, 2, 4, minus 1 times 5 minus 2, 4, 3. I'll have 3 times 5 is 15 and 2 times 4 is 8. 15 and 8 makes 23. Row times column. We'll have negative 6 and 6 makes 0. 20 minus 4 is 16, and then negative 8 minus 3 is negative 11. Nota bene. Remember, NB stands for the Latin phrase nota bene, which means note well. Every linear system may be expressed as a matrix equation. In particular, let's suppose that we let matrix A be A11 through A1n, AM1 through AMN. Let's let X with a half arrow over the top be X1, X2 through Xn, and let's let B with a half arrow over the top be B1, B2 through Bm. Now, I want to consider the matrix equation AX equals B. Also note that X and B are vectors. Yes, they are column vectors. And if I just use the word vector, that implies that I'm looking at column vectors. What is A times X? If I take the first row and multiply it by the first column, I'll get A11x1 plus A12x2 all the way down to A1nxn. That's going to be equal to the first entry in the matrix B. If I multiply the second row, I'll get A21x1 plus A22x2 through A2nxn equals B2. And this will keep on going until I have AM1x1 plus AM2x2 plus AMnxn, and that's going to be equal to Bm. As you can see, every linear system, which you can obtain by setting the first coordinate of the vector on the left equal to the first coordinate of the vector on the right, after all, one matrix is equal to another if and only if corresponding entries are equal. This will yield a system of equations. Every system of equations is representable as AX equals B. Remember the story of Dmitry Medvedev, who was a student of mine while I was in my postdoctoral studies at the University of California at Davis and teaching graduate level real analysis? When he told me that all of his quantum chemistry problems reduced to solving linear systems of equations, what he actually said was that all of his quantum chemistry problems end up being AX equals B. I want you to see a particular way in which we decompose the product A times X, because you'll be seeing this a lot throughout the rest of this course. Let's do a very special case. Suppose I have A11, A12, A13, A21, A22, A23, and I'm multiplying this by X1, X2, X3. Well, as you already know, you get A11x1 plus A12x2 plus A13x3. This is 2 by 3. This is 3 by 1. We end up with a 2 by 1. The next row is A21x1 plus A22x2 plus A23x3, our 2 by 1 matrix. But it's how I can decompose this that will be interesting. This is equal to x1 times the vector A11, A21 plus x2 times the vector A12, A22 plus x3 times the vector A13, A23. So I can think of this product as giving me a combination of the columns of this form. Whenever I take some vectors, and these vectors are the columns of the 2 by 3 matrix, whenever I take those vectors and take scalars times vector plus scalar times vector plus scalar times vector, that's called a linear combination. If, say, V1, V2 through Vn are m m by 1 vectors a linear combination of these vectors is an expression of the form C1v1 plus C2v2 plus CnVn, where C1, C2 through Cn are elements of the set of real numbers. Or scalars, they could be complex numbers more generally. Also, the column vectors of a matrix A, which has entries lowercase aij, are A11, A21 through AM1, A12, A22 through AM2. As you can see, we're just taking columns of the matrix. A1n, A2n, AMn. These are the column vectors of the matrix. What we've seen is that AX is the linear combination So whenever I multiply a matrix times a vector, what I get is a particular linear combination of the columns of the matrix A. I want you to know that. Now I want you to see something. Suppose I have 1, 2, 0, 4, and I multiply that by, let's say, 3, 5, 1, 2. Let's call this the matrix A and this the matrix B. What do I get? 3 and 2 makes 5. 5 and 4 makes 9. 0 and 4 makes 4. 0 and 8 makes 8. What happens if I multiply B times A? That's going to be 3, 5, 1, 2 times 1, 2, 0, 4. 3 plus 0 makes 3. 6 and 20 makes 26. 1 and 0 makes 1. 2 and 8 makes 10. So I want you to see something very important. As far as matrix multiplication is concerned, it is not always true that AB equals BA. In fact, more often than not, AB does not equal BA. Dun dun dun. What does this mean? Nota bene. Matrix multiplication is not commutative. There is no commutative law of matrix multiplication. It is not commutative, and that's the reason why this is the basis for so much quantum theory.
Consider the following example. When I enter a matrix A, it's going to be a 2 by 2. What are the entries going to be? How about 1, 3, -1, 2? And I also want to enter a matrix B, so I'm going to come down and edit matrix B. It too is going to be a 2 by 2. Let's make that to be 2, 1, 0, 1, 1, 1. So now let's multiply matrix A times matrix B. Just hit enter and you've got it. That's matrix A times matrix B. But let's suppose I want to do matrix B times matrix A. Note I get something totally different. A times B is not the same as B times A.
Speaking of quantum theory, I should give you a little bit of notation. In quantum theory, if you have a vector B, B1, B2 through Bn, at least in finite dimensional cases, instead of writing this as B with a little half arrow over the top, you'll often write this as a ket. This is called a ket. So column vectors are kets. If I have a vector B, which is a row vector expressed as B1, B2, and so on, again in finite dimensional real examples, that's often denoted by B with a set of brackets in this form. This is called a bra. So every row vector is a bra and every column vector is a ket. This gives you the bra-ket notation. We've seen one very important property of matrix multiplication that maybe is counterintuitive. AB does not equal BA. Matrix multiplication is not commutative. Well, what can it do and what other things can it not do? We need to know. A basic theorem giving properties that are valid for matrix multiplication is as follows. First of all, matrix multiplication is associative. But it has another form of associativity. Once you introduce a new operation, you need to describe how it behaves in terms of other operations that you've seen already. What if you have a scalar C times AB? Can you associate that scalar in different ways? And the answer is yeah. You can associate it with either of the factors in the product. What about matrix multiplication with matrix addition? It distributes, but you do need to be careful. It distributes, if A is on the left, then it will distribute on the left. If A is on the right, then it distributes on the right. So, what is it that matrix multiplication can't do? Let's suppose I give you the matrix 0, 1, 0, 0, that's A, and the matrix 1, 0, 0, 0, that's B. What do I get when I multiply these matrices? One is only multiplying onto the second coordinate here, so I get 0, 0, and then 0, 0. So in this case, A times B is the zero matrix. This tells us something very important. Note that A is not the zero matrix, and B is also not the zero matrix. This tells us the zero product theorem is false for matrices. Dun, dun, dun. You can have a product of two matrices be the zero matrix and both of the factors be non-zero. This is a very fundamental problem. For solving matrix equations, if you have A times B equals 0, that doesn't mean either of the factors is the zero matrix. Just as importantly, we already know this is the zero matrix. But if I replace the matrix 1, 0, 0, 0 with 0, 0, 0, 0, Notice I have A times B equals A times C because the products on both sides give me the zero matrix. But it is not true that B equals C. So you can't just cancel a matrix off of both sides of an equation. Dun, dun, dun. The cancellation principle is false for matrices. You can't just go canceling matrix factors off of both sides of an equation. Let that be a warning to you. Take very careful heed. You can't do some of the things that you are inclined to try to do. You're going to have to think carefully about what you can and cannot cancel from two sides of a matrix equation. To further develop the theory, you need to see what happens if I multiply 1, 0, 0, 1 times any matrix A, B, C, D, E, F. If I multiply the first row onto the first column, the 1 multiplies the A and the 0 multiplies the D. So I end up with just A. First row, second column, 1 times B and 0 times E, that just gives me B. 1 times C and 0 times F, and then when I multiply the second row, I'll have 0 times A and 1 times D, 0 times B and 1 times E, 0 times C and 1 times F. This matrix is behaving in a very interesting way. If I multiply that matrix by any 2 by 3 matrix, I end up with that other 2 by 3 matrix. Let's take A, B, C, D, E, F and multiply it by 1, 0, 0, 0, 1, 0, 0, 0, 1. What do we get? We'll take the first row and multiply it by the first column. Everything except for this A is hit by a 0, so we just end up with A. If we take the first row and multiply it by the second column, only the B will remain because everything else is multiplied by 0. First row times third column gives us only the C. Multiplying the second row times the first column gives us only the D, and then E, followed by only the F. There's something interesting that's happening with these matrices with only 1s on the diagonal and 0s everywhere else, which we can very informally write in this way. The n by n identity matrix is denoted by I sub n, or just I if there's no ambiguity on the particular application, and defined by I sub n is 1, 0, 0, 1, 0 after that, and we end up with 1s on the diagonal and 0s everywhere else. So it's a diagonal matrix with only 1s on the diagonal and 0 everywhere else. We'll often just write 1, 1, 1 with 0s everywhere else. Note, if A is m by n, then the m by m identity matrix times A gives you A, and A times the n by n identity matrix also gives you A. Why do we use this word identity? In algebraic systems, an element that behaves like 0 is called the additive identity. An element that behaves like 1 is called a multiplicative identity. When we're talking about the identity matrix, we're thinking of it in terms of a multiplicative identity. But you should notice, the matrix A might have a different identity on the left versus identity on the right. Now that we've expressed linear systems in the form AX equals B, we can prove the following theorem. A linear system of equations may have exactly one solution, 2, no solutions, or 3, infinitely many solutions. Let's prove this. If there is only one or no solutions, then there's really nothing left to prove. Here's the key. Suppose a system represented by AX equals B has 2 solutions, x1, x2, and let's suppose that they are distinct so that x1 is not the same as x2. Our goal is to prove that if the system has 2 distinct solutions, then it must in fact have infinitely many. Here's our plan. Set xh to be x1 minus x2. Then note that xh is not the 0 vector because x1 and x2 are distinct. Set xc to be x1 plus c times xh. This will give us a one-parameter family, hopefully, of solutions. If these are all distinct, then we will have infinitely many solutions. Note that AXC is equal to AX1 plus C times AXH. Well, we said x1 is a solution, so that must be equal to B. AX1 must be B because x1 actually solves the system. X sub h is x1 minus x2. This gives us AX1 minus AX2. But remember that x1 and x2 are solutions to the system AX equals B. And so you get B minus B, which gives us 0. That's the reason I chose the notation x sub h. A times x sub h is the 0 vector, which means x sub h is one of the homogeneous solutions. C times 0 is the 0 vector plus b is b. That shows us x sub c is a solution for any c. Now, how do I know all of these x sub c's are different for different values of c? Suppose c1 is not equal to c2. Also suppose that xc1 equals xc2. What does that mean? It means x1 plus c1 times x sub h equals x1 plus c2 times x sub h. You can see the x1s will cancel, and I'll have c1xh equals c2xh. This equation can only hold. Now, xh is not the zero vector, which means now xh is not the zero vector. So at least one of its coordinates, xhk, is not 0 for some k. This equation then implies that c1xhk is equal to c2xhk, and this is at the level of real numbers where the cancellation principle does apply, and that implies c1 equals c2. Now that is a contradiction that c1 does not equal c2, so we must have made some false assumption somewhere along the way. The only assumption that we made was that xc1 equals xc2. We deduce, therefore, that xc1 does not equal xc2 whenever c1 does not equal c2, and that means there are infinitely many solutions. In the proof of this last theorem, we assumed the opposite of what we wanted to show, and then showed that that led to a contradiction. And if the opposite of what we wanted to show was false, we deduced that what we wanted to show must in fact be true. This is a type of proof called reductio ad absurdum, also known as proof by contradiction. What is the transpose of a matrix? First of all, the transpose is denoted by A with a superscript of a T. It's defined in the following way. The ijth component of the transpose is equal to the jith component of the original matrix. What we're getting at here is that the transpose reverses the roles of rows and columns. So for example, if I have 1, 0, 3, 5, 7, 9 transpose, what I get is 1, 0, 3, 5, 7, 9 by reversing the role of a row and making it into a column. The row is made into a column. The matrix A is called symmetric if A transpose equals A. So for example, if I have the matrix 1, 3, 3, 5, I'll convert a row 1, 3 into a column, and the row 3, 5 gets converted into a column. You can see the transpose is equal to itself. So this matrix is symmetric. You can see that a symmetric matrix will have to have same entries on each side of the main diagonal. We've introduced a new operation on matrices called the transpose. We need to know what its properties are. in particular in relation to the other operations that we've defined. The transpose can be distributed across matrix addition. If you have a scalar times a matrix and take the transpose, this scalar can be brought out of the transpose process. The transpose of the transpose is the original matrix itself. This should be no surprise. If you reverse the roles of rows and columns twice, you end up with what you had to begin with. Most important for you to understand is that when you take the transpose of a matrix product, it reverses the order. AB quantity transpose is B transpose times A transpose. The fourth property being most important and the least obvious, we had better prove it. Let's do the proof in particular of part 4. AB transpose is, by definition, first of all, the product. We have nothing to refer to but the definition of the product itself, which is the sum as k goes from 1 to p of aik, b, k, j, and then the transpose. The definition of the transpose is to switch the roles of rows and columns, and so we get the sum as k goes from 1 to p of a, j, k, b, k, I. Now I'm going to reverse the role, the position of these two factors. I'm going to write this as bki and then a, j, k. But note that this is the sum as k goes from 1 to n of b transposes I kth entry times A transposes k jth entry. Now it is set up like the product of B transpose A transpose. And that is the end of the proof. Note, Euclidean dot product of vectors u and v is denoted by u dot v and defined by u dot v is u transpose v, where the transpose applies to the vector u. Here, we're thinking of the vectors u and v as being column matrices. So, for example, suppose my vector u is the vector, say, 3, 4, and v is the vector 5, negative 2. Then u dot v is 3, 4 transpose times the vector 5, negative 2. When you take the transpose of a 2 by 1, you end up with a 1 by 2. When I take a 1 by 2 and multiply it by 2 by 1, I get a 1 by 1, or just a scalar. I'll have 15 minus 8 is 7. This is a 1 by 1 matrix, and hence is equivalent to something in R1, a real number. So note that 3, 4 dot 5, negative 2 was 15 minus 8, which was equivalent to the 1 by 1 matrix 7. We'll sometimes just write that as 7. This is sometimes referred to as an inner because the transpose was between the vectors u and v. There is something called the outer product, and in that case it's uv with the transpose outwards, like this. Notice that you'll have 3, 4 times the row vector 5, negative 2. This ends up being row times column, row times column, row times column, row times column. You end up multiplying a 2 by 1 times a 1 by 2. The ones match, so the product is defined. You end up with a 2 by 2 as your answer. So the outer product yields a matrix, the inner product yields a scalar. There are other inner products. So for instance, let's suppose I define the inner product of u and v to be, by definition, u transpose a times v, where a transpose equals a, so that a is symmetric. Note then that if I take the transpose of the inner product, this had better be a real number, it had better be the same as this thing itself. But what is it? It should be u transpose a v transpose. But remember, the transpose reverses the order of a matrix product. And so you end up with v transpose a transpose, u transpose transpose, which is just u. But remember, a is symmetric, which means you get v transpose a u, and that is the inner product of v with u. We see that for these sorts of inner products, defined by u transpose a v, the inner product of u and v will always be equal to the inner product of v and u, but only if the matrix A is symmetric. I like to demonstrate to my pre-calculus students that all of Euclidean geometry descends from the Euclidean dot product. In the Euclidean dot product, the matrix A is the identity matrix. You may choose A to be a number of different matrices and end up with different kinds of notions of length and angle as a consequence. Also, if you choose A to be something which looks like this, negative 1, 1, 1, 1 with zeros everywhere else, you end up with something that's not quite an inner product, but it does give rise to something very interesting, namely all of special relativity. Special relativity descends from those sorts of products, u transpose a v, where A is this matrix. Throwing in a negative like this makes a distinction between a time coordinate and your spatial variables. By the way, it's pretty easy to describe space-time geometries where you have two time coordinates and two spatial coordinates instead. In quantum theory notation, if I have a vector u which has coordinates a, b, remember u is equal to a ket. The corresponding bra is the transpose. So if I want to find the Euclidean dot product of a vector u and v, you know that that's u transpose v. That ends up being the bra for u multiplied onto the ket for v. When I write something like this in quantum theory, I'm just taking a dot product. More generally, in quantum theory, we sometimes put a matrix in between the vectors u and v. And then we end up with the same thing as U transpose AB, and we've seen that before.